Okay, we're continuing with section 1.2, modeling and alternative representations. Let's share the screen. Microsoft PowerPoint. Let's go to the next slide and talk about modeling and alternative representations. Modeling is one of the primary problem-solving methods in physics. You form an appropriate model of the problem, and the way the little blue box says, a model is a simplified substitute for the real problem that allows us to solve the problem in a relatively simple way. So as long as predictions of the model agree to our satisfaction with actual behavior of real system, the model is valid. If the predictions do not agree, the model must be refined or replaced with another model. Model reduces the complex problems to a limited number of classes of problems that can be approached in similar ways. A scientific method is a theoretical construct and may have no visual similarity to the physical problem. We need models because the universe is complicated. Imagine solving a problem about Earth's motion around the sun. Earth is very complicated with many processes occurring simultaneously: weather, seismic activity, ocean movements, human activities. The modeling approach recognizes that none of these processes affects the motion of Earth around the sun to a measurable degree. These details are ignored. So the size of the Earth does not affect the gravitational force between Earth and sun. Only masses of the Earth and sun and distance between them, the distance between their centers, determines this force. So in a simplified model, the Earth is imagined to be a particle, an object with a mass but zero size. Replacement of the extended object by a particle is the particle model. By analyzing the motion of particles with mass of the Earth in orbit around the sun, predictions of particles' motion is in excellent agreement with the actual motion of the Earth. Now, two primary conditions for using a particular model are this: number one, the size of the actual object is of no consequence in its analysis of its motion, and any internal processes occurring in the object are of no consequence in the analysis of its motion. Both of these conditions are in action in modeling the Earth as a particle. Excuse me. The radius is not a factor in determining its motion. Internal processes such as thunderstorms, earthquakes, and manufacturing processes can be ignored. There are four categories of models in this class. The first category is the geometric model. That's the first category, the geometric model. The form of geometric construction that represents a real situation. And it's a sets aside real problem and perform an analysis of geometric construction. Okay. Sorry about that, I swallowed wrong. Example, finding the height of a tree. You wish to find the height of a tree but cannot measure it directly. You stand 50 meters from the tree and determine that a line of sight from the ground to the top of the tree makes an angle of 25 degrees with the ground. How tall is the tree? Well, the figure shows the tree and a right triangle corresponding to the information in the problem superimposed over it. We assume that the tree is exactly perpendicular to a perfectly flat ground, not an assumption we can always make. In the triangle, we know that the length of the horizontal leg and the angle between the hypotenuse and the horizontal leg, we know these things. We can find the height of the tree by calculating the length of the vertical leg. We do so with the tangent function. The tangent is the opposite side over the adjacent side. We'll do a review of trigonometry at some point. So the h is Tangent theta is equal to h over 50 meters. So h is equal to 50 meters times the tangent of theta. 50 meters times the tangent of 25 degrees is 23.3 meters. Now, when you do these calculations, make sure that you are set in degrees and not in radians, or another popular mode is grads. Stick in degrees. We will get to the point where we'll use radians, but for right now, stick to degrees. So once you do all the calculations, you'll come up with the height is 23.3 meters. Okay. And I think, no, there's 2 more slides. Okay. From the modeling approach, once we draw the triangle in the previous example, the triangle is a geometric model of a real problem. It is a substitute. Until we reach the end of the problem, it is not about a tree, but a triangle. The vertical leg of the triangle represents the tree height. Examples of geometric models are the Earth is a perfect sphere. A pizza is a perfect disc. A meter stick is a long rod with no thickness. An electric wire is a long straight cylinder. The particle model example is the second the particle model example of secondary category models is the simplification model. The simplification model, details that are not significant in determining the outcome of the problem are ignored. It simplifies the problem. The simplification models will assume that quantities such as friction forces are negligible. They remain constant or are proportional to some power of the object's speed. We will assume uniform metal beams, laminar flow of fluids, massless springs, symmetric distributions of electric charge, resistance-free wires, and thin lenses. These are all simplifications. They aren't, if you get into the nitty-gritty details, these can't always be taken for granted. The third category is analysis models. It's an important technique in problem solving. Cast a new problem into form similar to one we have already solved, which can be used as a model. All of analysis models in classical physics based on 4 simplification models: particles, system, rigid object, and wave. The fourth category of models is the structural model. There you go. Generally used to understand behavior of a system different in scale from our macroscopic world, much smaller or much larger. So we cannot interact with it directly. Examples: the hydrogen atom is modeled as an electron in a circular orbit around a proton. Ancient geocentric model of the universe. Earth was theorized to be at the center of the universe. This is a model that was later abandoned, as you know. Okay. So alternative representations. A representation is a method of viewing or presenting the information related to the problem. Scientists must be able to communicate complex ideas to individuals without scientific backgrounds. You can use graphs, pictures, etc. Types of representation are a mental representation. From a problem description, imagine what is happening. Let time progress so that you understand situation and can predict what changes will occur in the situation. And this step is critical in approaching every problem. So basically, you take the problem to extremes. We'll do that, and I'll point it out when I am doing it in the future. A pictorial representation. Drawing a picture is useful to understand the problem. Example, in architecture, the blueprint, it's equal to a pictorial representation of a proposed building. Generally, pictorial representation describes what you would see if you were observing a situation. As an example, look at the left figure. It shows a pictorial representation of a baseball player hitting a short pop-up foul. The simplified pictorial representation often is useful to redraw pictorial representations by applying simplification mode. similar to application of the particle mode. In the pictorial representation of the Earth in orbit around the sun, you might draw the Earth and sun as spheres, with possibly some attempt to draw continents to identify which sphere is the Earth. In the simplified pictorial representation, the Earth and the sun are drawn as dots, representing particles with appropriate labels. The middle figure is a simplified pictorial representation corresponding to the baseball trajectory, a parabola. Notations Vx and Vy refer to components of the velocity vector of the baseball. The Vx is the horizontal velocity, and Vy is the vertical velocity. A graphical representation. For some problems, graphs can be helpful. Examples in mechanics, you can use position versus time graphs. In thermodynamics, you use pressure volume graphs. The right figure is a graphical representation of position as a function of time of a block on the end of a vertical spring as it oscillates up and down. We'll get to that when we study Hooke's law. It's helpful for understanding simple harmonic motion. A graphical representation is different from a pictorial representation. In graphical representations, the axis may represent any two related variables. As an example, the graphical representation may have axes for temperatures and time. The right figure, the axis are vertical position y and time t. So as time t goes to the right, you can see the displacement in y. Graphical representation is generally not something you would see when observing the situation. A tabular representation. Sometimes it's helpful to organize information in tabular form to help make it clearer. Making tables of known quantities and unknown quantities. You can list these in the table, and sometimes it'll help you visualize what's going on, such as the periodic table of the elements. Then there's mathematical representations. Ultimate goal in solving a problem often is represented by a mathematical representation. The goal is to represent a situation mathematically and solve for the desired result. Okay, this ends section 1.2 on modeling. The next section is section 1.3, dimensional analysis, a very important section. Dimensional analysis will help you know whether you're going in the right direction or not.